So this is about a book, a 20 Newton book that is standing on a table. Okay, it's just a book, nothing more. But the problem is getting information, valuable information. For example, it tells me that the book is 20 Newton. When it says that, it means that it's about the weight. The book's weight is equal to 20 Newton. And when it says stands on a table, means that it's just on a table, not moving, okay? It's just on a table. In other words, that there are no forces acting on the book because the book is just on the table. That's what it means, even if it sounds very obvious, okay? So, one other thing that is important is actually that the book is on the table, like the the open English, I think, a commercial that says the book on the table. Wow, a terrible song that that guy made. I have never used an example like this again because now I won't be thinking nothing more than that guy thinking the book's on the table. Anyway, the book is on the table, of course, but because it's on a table, the table represents a surface. Every time you have a surface, every time your objects of interest are on something, okay, on the ground, on grass, on a table, or whatever else, means that is being affected by a force that is implicit but is never mentioned, and that is the normal force. So for this example, all we need is to include the information provided in the exercise, the weight, but also by knowing that the book is on the table, you also need to include the normal force. Remember this, every time a surface is involved, okay, every time the object of interest is on a surface, you will include the normal force. Now, as you can see right here in the center of the object, I have a dot, a red dot. The red dot represents the center mass of the object. In other words, you will locate the forces in the center of the objects, okay? If you have a ball, for example, it's going to be also in the center. If you have a table, it's going to be also in the center. If you have a block, also in the center. Because in the center of the objects is the place where you find the center mass. The center mass is the place where the more mass is not just concentrated, but also it's balanced. It's like the center of your balance, the source of your balance. So let's see. This is a prior sketch that you do, and now we'll see how we do the free body diagram. For the free body diagram, you will need to draw, first of all, a Cartesian plane. It doesn't need to be too big, okay? So there you go. Here you have your your Cartesian plane. To represent that this is a free body diagram, you can use FBD instead. Now, my book, I'm not gonna draw it here, okay? Because it's going to take longer to do that. So all I'm gonna do is I will represent my object with a center point, just like I did over here. That point in the center means that this is my book, okay? But now all you see is a center. Now, In this Cartesian plane, you will include all the forces acting on the object. The force that is going down is known as the weight. Because it's going down, you put the direction downward. And of course, you have to name the force. This force is the weight, and the weight will represent weight by the letter W. Now, remember, the book is on the table. Table. The book's on the table. Because it's a table, you must include a surface, okay? Because it's a surface, you must include the normal force. But the normal force is always going up. So you put it over there. And to indicate that this is your normal force. Remember, you will include a curly end to represent a normal force. Because it's going opposite to the weight, and the forces must be balanced, the normal force will also be equal to the weight. And that will be it. That will be it for the object. Xavier?
Miss, in W, why is not negative 20 if it is going down?
It's not that it's not negative 20. Yes, it is negative 20. But you see the negative? Because it's going down. You already said it. Okay? So the normal, it's like it's going up. And because it's going up, it's going to be positive. It's implicit in the sketch. You don't see the negative or the positive here. But just by taking a look to the direction, you will know that the normal is positive because it's going up, and the weight is going to be negative because it's going down. Even if it's not in the sketch, that's like the analysis that you must do. Okay?
Okay, thanks.
You can put the directions if you, but I mean, it's not necessary that you put the directions since you see the directions here. And you see the direction over there. I mean, that's the purpose of the free body diagram, to represent in a single sketch all the forces that are acting in the direction the forces are going. Just remember this. If it goes up, it's positive. If it goes down, it's negative. If it goes to the right, it's positive. If it goes to the left, it's negative. Now, it's not always going to be negative. For example, if it goes up, it's positive for y because it's just moving in y. If it's going down, it's negative for y because it's moving vertically. If it moves to the right, positive, but it's only moving in the x-axis. And if it goes to the left, it's negative. But it's negative because it's moving to the left in the x-axis. Just remember this. Vertical is y-axis and horizontal is x-axis. And each of them have a specific sign. Now, this example is very simple, so maybe we can try with different examples for you to get used to it. Okay, first example, book on the table, easy. Let's work in the second example. It says, draw a free body diagram to sketch the following examples. The first one says, a pushing force of 100 Newton is exerted on a shopping cart that has a 50 Newton weight. So first of all, we need to identify the object of interest. In this case, we're talking about a shopping cart. So that's what this sketch is going to be about. So I'm just going to do here a shopping cart, okay? ¿Por qué sales así, amiguito? Okay. Okay. Okay, there you go. You have your shopping cart right here. Not the best, but it works, okay? Está raro eso. Anyway. So it says a pushing force of 100 Newton is exerted on a shopping cart. So the problem is it mentions the kind of force that is acting on it. It says a pushing force. Okay, where is the pushing force going? Is it going like A or like B, in your opinion?
A.
A.
Yes, it works in A because normally when you go to the supermarket, this is the way you use the cart, okay? If you are a very small kid, very young kid, probably you will be thinking about B because kids, that's what they do. But normally, I mean normal people, use the shopping cart like in A, okay? So we're going to be working in this. Because we are pushing the cart is going to be moving to the right, okay? And the force that is acting on it is a force that is 100 Newton. And it says that it's a pushing force. So I indicate that it is a pushing force. Then it says the shopping cart has a has a 50 Newton weight. Okay, so the other force that is acting here on this object is the weight. And remember what we said. It comes from the center of the object downward. This is the weight and is 50 Newton. Now, I ask you something. Is the shopping cart on a surface? Yes or no?
Yes.
Yes, I mean that's how you move a shopping cart, over a surface, okay? Over the ground, for example. So it's on a surface. This is important that you include it. So this is your prior sketch. It doesn't need to be perfect at all. Nothing, okay? Nothing perfect. But the one that needs to be a lot better is the free body diagram. So the free body diagram, we start with the Cartesian plane. Okay. The shopping cart is going to be here in the center. And now I will include all the forces. the first force that is acting on the object is the pushing force, okay? So I'm gonna put it here. But let me tell you something. You can put the force like A or like B. Both are correct. But what really matters is that you include the direction of the force. This pushing force is going to the right, so the arrow that represents the force must be going to the right. Now, I prefer A because, in my opinion, A represents better this situation. Okay? The object is being pushed. So I think A is more accurate. That's why I choose A. But in the end, if you use A or B, both are going to be correct. Now, I prefer, as I told you, I prefer A because I think it's more accurate. It represents the situation better. So, in my opinion, the force is here and is a pushing force. Now, my object has a weight, and this weight is always mandatorily going down. Okay? So the weight, you will represent the weight like that, and you will include the data about it. It is 50 Newton weight. Okay? Now, as we were saying before, it is a cart. It's on a surface, and every time objects are on a surface, the normal force is also acting on the object. Now, where is the normal force going? Is it going to the right or is it going up?
Up.
It's going up. Okay? So here, you put your normal. Remember, it's a curly N. And it must be balanced with the weight. Okay? Let me tell you why it needs to be balanced with the weight. The weight is pushing you down the ground, okay? If there were no normal, okay, imagine that this is the ground and you are standing here. Okay? So, on you, there's acting the weight, okay? The weight is keeping you here on the surface. That's what the weight does, okay? But if only the weight is acting on you, you will be going down the ground by just the action of the weight, okay? So this weight is gonna be like pushing you down until you are below ground, okay? And that doesn't happen. That's why you are able to walk on a surface, to run, or just to sleep over a bed. Yes, gravity is pushing you down. That's why, on your favor, to balance this force, this downward force, to balance this force, to avoid pushing you below ground, we have this normal force that is keeping you on the surface. And it balances the weight. That's why the normal force is gonna be, in this case, equal to 50 Newton, sorry. Just remember this. The normal is what's keeping you on the surface. That's why a ball bounces, okay, when you're playing basketball. What happens when you play basketball? The ball bounces, okay? So, here, the ball is being affected by gravity, by its own weight. That's why it goes down. But it bounces back because it exists the normal force. This is what we know as action-reaction law, and it's related to Newton's third law of motion. Okay? So, sorry. I know that I always take my class further. The reason is because I want you to understand the concept of normal, because we don't see it. It's not like we can see forces. We cannot. Yes, we can measure a force, but we cannot see it. I can push an object, I can throw an object, I can kick an object, but I don't see the force. But you can imagine where the objects go by just picturing the situation on your mind. But a normal force is very difficult to imagine. That's why I try to use more examples. Now that will be it. Okay, this will be all the free body diagram for the shopping cart. Now, in the second example, we have a 5 Newton apple that is motionless on my desk. Okay, so first what I do is I do my prior sketch. So there I go, I have my apple over here. Okay, and it says that this apple is motionless. Motionless means that it's not moving. If it's not moving, means that there are no forces acting on the apple. Okay, I mean, I'm not pushing the apple with my finger. No, I'm not doing that. So the apple is just on the desktop, motionless. Because it is on the desktop, what force is acting on the apple?
Gravity.
Gravity, which is the force due to gravity. This is the center of my apple, and the gravity is pushing the apple down, and it causes a force that is called weight, and this weight is 5 Newton. Now, because the apple is on a surface, what is the other force that you have to include in the diagram?
Up.
Up is coming. How do you call this force that is coming up? And how much is that?
It
Javier?
is opposite,
Is opposite.
and it will be the same, but
It
in
will be.
positive, but it's implicit.
It is positive, it's implicit, I don't have to include the sign, but the name of the force is called normal force, okay? Now, this is your sketch, and now all you do is the free body diagram in the Cartesian plane. In the center, you have the apple, Coming down, you have the weight. And going up, you will have the normal. Nothing more because the object is not moving. Newton up, no need to include the signs because it is already implicit in the arrow. And that will be it. As you can see, this is the simplest situation. It's the same situation of the book. So even though the object changes, the situation changes the weight, but the sketch is the same. The only difference is the value of the weight. That will be it. And then Messi kicks a 25 Newton football with a force of 180 Newton to the right. There is a friction force of 35 newtons due to grass that is exerted opposite to the football's motion. So what is my object of interest in this example? What is my object of interest?
The football.
The football. I don't care about Messi. Yes, he won the Copa America, but in this example, Messi is not important. What is important is the football, okay? The ball itself. So we can try with a sketch of the ball right there, and we must include the forces. What is the kind of force that Messi is applying to the ball? Is it a pulling force or is it a pushing force?
A pushing force.
Exactly. So take a look. This is the center. In the center I trace a dot. This dot represents the center of the object. And here I will put all the forces that are acting on it. So Messi kicked the ball with a force of 180 Newton. And it's a pushing force. Okay? Now, that ball, what is the weight of the ball? Is it 25 Newton or is it 35 Newtons? What is
25.
that? 25. 25 Newton ball is like saying un carro de una tonelada. It's like that, okay? So we're talking about a 25 Newton football, okay? So this will be the weight. And the weight is always coming down. Now, the ball, is it on a surface? Yes or no?
Yes.
Yes, it's on grass, okay? So, because I have a surface, I have to include what force? What force I need to include? If a surface is involved, what is the force that I need to include?
Normal force.
The normal force. The normal force is coming up, okay? And because it's balanced with the weight, it's gonna be also of 25 Newton, but it's going up. Now, the exercise also mentions, okay, we already include a force of 100 Newton to the right, okay? But there's another force that is mentioned, and it is friction force of 35 Newton. It says, this is the first time that we work with friction in an exercise, but it says that this friction force is exerted opposite to the football's motion. Sorry about it. it says is exerted opposite to the football's motion. So if Messi kick the ball to the right, where is the ball going? If I push an object to the right, where is the object going? To the right or to the left?
To the right.
Okay, so this object will accelerate in the right direction. So when it says the friction goes opposite to the football's motion, that means that the friction comes in the opposite direction. And you represent friction with an F, a cursive F. Then all you do is the Cartesian plane and include all the forces. So down you have the weight 25 Newton. To the right you have 180 Newton. Up you have the normal. And to the left you will have the friction, and is equal to 35 newtons.